Our next speaker is Robert Hampton, and Rob is going to talk about metacognition and memory systems in primates.
Attention for a half hour here, and I really want to thank the organizers for inviting me on this trip to come to Bangalore. It's great. I'm really enjoying myself, and I'm enjoying the conference. So what I want to do today is tell you a little bit about what one of the lines of research that we pursue in my lab with non-human primates. These are the human primates. You'll see some non-human primates in a little bit. And one of the things I want to talk about that I think is relevant to some of the issues we've been talking about, although maybe not decisively relevant, is some studies we do of metacognition and memory in primates. So a phenomenon that I think most of you are familiar with, but I want to make sure we're all sort of on the same page as I get started here, is the idea that there are at least two types of knowledge that we know about in humans. And those are implicit, or what we people in this room might generally refer to as unconscious knowledge. And the property of that kind of knowledge is that it's inaccessible to other cognitive systems. So certainly verbally and in many other ways, we don't know that we have that knowledge, although we can express behavior that proves that we do have that knowledge. And this is contrasted with explicit knowledge, which is accessible to introspection. So we can say, yes, I know about that, and you can make predictions about your own behavior, for example, that are fairly accurate based on your explicit access to that kind of knowledge. This distinction is manifest in this kind of very familiar human memory taxonomy that Larry Squire and Howard Eichenbaum and other people use, where we say that memory is at the first bifurcation here, divided into explicit system that includes semantic knowledge about the world, and episodic memory about personal events, and implicit memory, which includes a bunch of different systems that probably all have distinct neural substrates, including priming and habit and skill learning. And so one of the sort of general questions that we have in my lab is whether this kind of taxonomy as it exists in humans, and certainly it is subject to modification as we go along here, but whether we can see those same kind of divisions and dissociations and the presence of these systems in other species besides humans. And it's very problematic that when you start looking at this taxonomy, the first distinction that is made at the top is between implicit and explicit, and that's something that can be difficult to capture, as we've seen already this morning in non-human animals. But the argument that I want to make is that, at least in some situations, and these have to be, I think, fairly carefully constructed experimental situations, metacognition, or that our knowledge about our own knowledge, or our cognition about our own cognition, can be used to assess whether memories are accessible, and therefore explicit. So accessible memories are those that can be monitored and controlled. So I'm going to tell you a little bit about what we think we've shown in monkeys about monitoring and the control of memory. And again, just to make sure that, well, my slides aren't advancing. To make sure that we're sort of on the same page about this, I want to give you one example of this dissociation that's well known in humans and was first clearly documented in a patient named H.M. who died recently. H.M. had gotten had his hippocampus and some other parts of his medial temporal lobes removed bilaterally to treat epilepsy in the 50s. And a very tragic and amazing property of this person was that he went through life from then on unable to form new explicit memories. So he didn't know what had happened to him since then. He had a great deal of trouble learning, that his parents had died. He wasn't able to update information about the world, although he did continue to remember all the things that had happened to him before his surgery, which is interesting. So it shows the capacity for retrieval was there. He just couldn't form new memories of that nature, of the explicit nature. But what's interesting is HM was tested in a situation like this, where you do a mirror writing task, and what you're seeing here is a subject who is to take a metal stylus and trace this pattern here without touching the boundaries of the pattern, and he can't see his hand directly. He sees his hand in a mirror. And so this is a difficult task because everything you would do, normally you have to do the opposite with respect to your visual perception. And so it takes a little while for people to get good at this, and you show a gradual acquisition of that. And HM shows an acquisition, or did when he was alive, that looks just like a normal person's acquisition. So he gains this skill He shows he's encoding new information and got a new kind of knowledge, but he will deny ever having done it before. When he comes back the next day, indeed, 10 minutes after he's left the room, he won't remember that he practiced this, and he would say that he doesn't know what he's doing. You just say, well, try it. And when he tries it, then he can do it quite well. So you see this remarkable dissociation between an unconscious kind of knowledge that he has and his conscious access to it, which is absent. So one of the things that we want to know is whether there are other species that, like humans, are aware of some, but maybe not others, of their memories. So I want to just orient you to how we think we can approach this problem, because I do think it's a difficult problem. And I'm going to say, I want to say one thing about, I use this term non-human animals all the time, and I don't actually mean that as a way of a priori creating a distinction between us and other animals. I actually mean it to say that we are animals and there are other animals, and what I'm talking about is the ones that aren't human. So how do we approach this problem? Well, we try to take a functional evolutionary approach, which I hope will come across in these couple of bullet points here, that the explicitness of that access that we have to explicit memory is a phenotype. So it's a phenotype like any other phenotype that you might think an animal had, either cognitive or physical. And by that I mean that it evolved by natural selection. That's how it came about. And the important point there is that natural selection acts on overt behavior. Natural selection is not going to respond to your phenomenal experience unless that has some consequence in your behavior that improves your ability to survive and reproduce. So this access must be doing something for the animal. That is, memory access must serve a function. Animals that have it can do things that animals that don't have it cannot. And if you accept that statement, then you start thinking, what is it that they can do? You can create an experiment that asks, do the animals do this thing that we would think they would do if they had access to their memories? And one of the things that I think access gives us is the ability to respond adaptively to ignorance, so it can correct our ignorance. One way it might do that is it lets us avoid situations where the knowledge we need to behave appropriately is absent. Another way it might work is that when we recognize this ignorance, we can gather or maintain needed information that's going to help us. I don't know why my computer is deciding not to advance sometimes here, but eventually it will, I hope. There we go. And the other thing that it helps us do is adaptively control retrieval processes and collect information from our own memory stores that's appropriate for a given situation. Okay, so I just give you an example of a kind of design that we use all the time in my lab that shows that animals, definitely non-human animals, primates in particular, certainly do have memories. We do these kind of experiments all the time. Animal sees a picture at the beginning of a trial. This is called a match-to-sample procedure. There's a delay period where the animal has to remember what it saw, and then at test they're presented with that item and some distractors, and they have to choose the item that they saw at the beginning of the trial. Hopefully everyone remembers the car. Oh, this is troubling. All right. So one of the things we know about this performance in monkeys is it's dependent on a region of the brain called the perirontal cortex that's shown here as part of the temporal lobe memory system. And we know that because when we, in monkeys that are lacking that part of the brain, as seen in this MRI here, where you can see a very small bit of tissue that's removed from the temporal lobes, those monkeys show unusually rapid forgetting of these images in these kind of experiments. So what you see up here is the performance of normal monkeys across delays from 0 to 32 seconds, and their performance remains quite good. But these guys with the perirontal cortex removed, they forget very quickly something that they've seen recently, although they do perceive it pretty well because they're doing well at a short delay. It's just that they forget rapidly. So we can see that, yes, there's some deficit in memory here, but is it possible that we have multiple systems here? And I'm just giving you one example. There are many, many, many studies that show that there are multiple memory systems in a variety of animals. But so we want to look for some other performance that's intact at the same time that this performance is impaired. And I'm going to show you a procedure that we've been using in the lab, and this has been worked on a lot by my postdoc, Vicky Tu, recently. And I'll give you an example that'll be familiar to the more senior members of the group and less familiar to the younger members of the group. But it's the problem of where are my keys when I'm trying to leave the house in a hurry. And imagine the situation where you normally leave your keys by the door. You have a hook by the door saying that's your typical thing to do. Well, so you've developed a habit of always looking for your keys by the door because that's where you normally keep them. But you also can remember that, okay, when I came home last night, I put my keys by the door in the normal place. And using this kind of logic that's been developed by Larry Jacoby called the process dissociation procedure, you think about these two systems now as being congruent. That is, they work together. Your habit and your memory, they tell you to do the same thing, get your keys by the door. On contrast, you might have come home and somehow something funny happened. The dog had to go out or something, and so you didn't put your keys in the normal place. You left them on the desk instead. So now your habit is still there from all the previous days where you normally put your keys by the door, but you also could remember that I put my keys on the desk last night. And so now you're in a rush to leave, and the question is what wins out, your habit or your memory? And again, the more senior among us will probably have had the experience that sometimes your memory doesn't win out, unfortunately, and you look in the wrong place. It can be a little frustrating. This is a situation where habit and memory are incongruent, so now they're giving you a different answer. What's neat about this that Larry Jacoby worked out is we can use this as a nonverbal way of trying to ask about processes in memory that are controlled and automatic in both humans and non-humans by asking what's the probability, using this analogy of looking by the door. And the way you can think about it is that in the congruent case, the probability of looking by the door is the sum of the extent to which you remember and the extent to which you forgot, but your habit is present or strong. In contrast, in the incongruent condition, the only reason you're going to look by the door when you didn't put it by the door is when your habit is winning out and your memory, that's 1 minus memory, has been forgotten. The nice thing is this incongruent term substitutes in the equation, and we can solve for memory and habit. So we model this. Of course, the monkeys don't have keys that they need to remember, but we can create a situation like this by using the match to sample design I just showed you, where we give the animal a sample at the beginning of the trial, then at test he sees that sample and several distractors. Normally what we would do then is on the next trial you would randomly pick one of those images to be the sample and give him a new test. But what we can do to create a habit is we bias the choice of the sample so that one item is the correct answer much more often than the other items. And then we can give congruent and incongruent trials where either the habitually presented stimulus is the sample or a different one, and we ask how they perform. And the interesting result we get is with these monkeys that have the parietal cortex removed, shown in red, their memory score is very low, but their habit score is completely intact. So it looks like their habit system is a separate system from the one that's affected by this part of the medial temporal lobe. Well, so that might be convince you that there's some parallel in humans and non-humans in these kind of memory systems, but what we really want to move on to is ask whether these are explicit and accessible memories as they are in humans. And so one design that we've used to look at this, again, uses the master sample paradigm, but we show the animal something to remember. Later he's going to get a test. If he gets it right, he gets a peanut, and the peanut is something that a monkey really is happy to get as a reward. What we add in here then is a judgment phase where at the end of the interval, the animal has a choice between taking the test and avoiding the test. So this is not what's typically done in these experiments. Normally we just force the animal to take the test, or at least put them in a situation where the only thing he can do is take the test. And so we don't really know what they know about their own knowledge state. This gives us a little window on that. So if he chooses this side of the screen, he's going to get a test, and if he's correct, he'll get a peanut. That's a good thing, but it's a gamble because you're only going to get the peanut if you remember. If you get it wrong, you get nothing, so that's a bummer. If you choose this side, you can instead of taking a memory test, you can just get a primate pellet, which is not as desirable as a peanut to the monkey. So it's kind of a gambling scenario where if your memory's good, you should take the test, and if it's not, you should avoid it. Well, you give monkeys this situation, indeed they take the test, sometimes avoid it other times, but you still don't know that they're doing that appropriately. You just know that they're dividing their choices. You have to make it a little bit more complicated by having some trials now where they don't have a choice. They have to do the same thing they do on every trial that they choose, but they're just going to go take the test. And what we're going to do then is look at the accuracy on these trials where the monkey has no choice but to take the test, and compare it to the accuracy on trials where he chooses to take the test. And if he's selecting trials on which his memory is good when he has the choice, he should do better on those trials than on the forced trials, and that's indeed what we observed. I'm going to show you some videos later, but I'm going to skip these, hopefully. So that's indeed what we observe. When you look at the trials where the monkey is forced, they're slightly or somewhat less accurate than they are on these freely chosen tests. And this difference in this graph is not huge, but one thing you have to remember is that these trials where they're forced, they include trials that the monkey would have taken anyway. And so it's an average of those types of trials. And we've taken multiple other manipulations to support this contention that they actually can tell the difference between a good memory and a bad memory. But rather than show you those, I'm going to show you some other paradigms that we have used to look at this. So another question we want to ask is whether monkeys will seek information that they need when they're ignorant, in addition to bailing out when appropriate. And this is based on work that was done by Joseph Call and Melinda Carpenter. I think you're going to see a little bit more of in the next talk. But what we do, based on the design that Joseph developed, is we create two situations for the monkey, one where it knows where some food is and one where it doesn't. In this case, the monkey's going to watch the experimenter bait one of these tubes with an M&M, which again is something the monkey's really excited to get. And you'll see what the monkey does. He reaches immediately when he gets a chance, and he collects that reward. Now, important thing about that apparatus that you saw is that those are metal tubes. The monkey can't see where the M&M is. He can see where it was put, but not where it is. And it's got a mechanism so that when he makes a choice, it locks down and he can't make another choice. So again, you only want to make a choice if you know where the food is. So in another condition, we make it so that the monkey doesn't know where the food is. So the baiting takes place while an opaque screen is down, and then we record what the monkey does in this condition. I think you'll see that it's rather different. So he really differentiates his behavior depending on whether he knows or does not know where that food is. And when he doesn't know, he collects information before acting. One of the things that's interesting about this is that you have to press him to do that. If it's easy to look, he'll just look all the time, and then he's guaranteed to get the M&M every time. But if you lower that tray down so he has to really bend over, doesn't want to do that, then he starts differentiating and being careful and only looking when it's necessary. This just shows that occurs in a whole bunch of monkeys. You do have a few monkeys that this monkey Galileo, he just never gets it. So there's variability just like there is in humans. And then you've got this monkey Flamsteed. He does not want to lose an M&M ever, and so he always looks no matter what. Those two trials. Well, we give him the option here now. When the test appears, if he touches the arrow on the right, he's going to go down and get his test and has to pick the appropriate place to get the reward, or he can choose this sort of recycle symbol, and that refreshes his memory about where the dot is. And to control their use of those, they have to touch them a certain number of times. If they're using one too much, they have to touch it a lot, and that discourages use of that. So again, like in the former experiment, what we see is that the monkeys are much more likely to get asked for the refresher when they haven't seen where the dot was. So they recognize that they don't know and collect information. Then what my student Ben did with this paradigm is then he varied the delay. You can see these delays are quite short, but it's actually, when you do 1,000 of these trials in a row, it's difficult to remember where the target is. So they'd been trained at 1 second, and we gave them shorter durations and we gave them longer durations. And what you can see is their performance drops off as the durations increase and their information seeking increases. So it's not just whether you saw a dot or not, it's whether you remember the dot that drives the information seeking. So I told you now about some experiments that show the monitoring of memory, and I want to now turn to the other side of metacognition, which is the control of memory, and give you some ideas of the things that we've been doing with that. So we showed that monkeys monitored their memories and avoided trials where they forgot what they saw, and they also sought information when they were ignorant. But so are they able to engage in some active cognitive control of memories? For instance, can they call memories to mind or actively maintain information during a memory interval? So again, this is work of my graduate student, Ben Basil, and what he's been looking at is the difference between recognition and recall. And so recognition is the format which we almost always use in non-human animals. That is, we show them something, later they see it again, and they have to pick it out from some distractors. This guy's picking out an apple he saw earlier. And this contrasts with recall, where you don't get to see the item again. You just say, well, what happened, or what did you see before? Or I gave you a list of words, tell me the words that were on that list, or write them down on a blank piece of paper. There's no cues there to trigger a recognition. You just have to pull these things up from memory. And again, nearly all the tests with non-humans use recognition rather than recall. So Ben wanted to develop a recall task, and he based it on something called the Ray-Osterioth complex figure task, which is just simply you show subjects, in this case many times patients, these complex figures that are pretty meaningless. They copy that at a study period, and after a delay they reproduce it, and you can score how many of the elements they reproduce and measure their recall. Well, that's a little bit complicated for the monkey, but what we did instead is we show them a simple array of pixels that they study by touching, and then after a delay they have to reproduce that on a touch screen. So the paradigm looks like this. Again, you see this, you start the trial, you see the sample, delay happens, one of the pixels appears, and you got to complete the array. And we contrast it with a recognition format that uses exactly the same stimuli under exactly the same conditions. They see a sample, there's a delay, they just have to touch this single box to produce a test, and at the test you see an item, and then this thing that says, no, that's not the correct item. So if it's the thing you saw at the beginning of the trial, touch that. If it's not, touch not the thing I remember. Let's see if I can show you a video of a monkey doing that. Take your time. Okay, so when he completes that picture correctly, he gets a reward. And what Ben found that's pretty striking here is that we got this nice parallel between what we see in humans with the contrast in recognition and recall. So the first thing is just the monkeys can perform in this task. It's not easy for them, but they can do it. But the second fact is when we do recognition trials where you represent the trial, the stimulus that they saw at the beginning of the trial, and we contrast that with the situation where they have to just reproduce it from memory, we get the same thing that we get in humans, which is that it's easier to recognize than it is to recall. And we know that from, say like a multiple choice test, that's, especially one that's not well designed, is easier than an essay test where you just have to generate a lot of information from scratch. So we're interested that we got this very nice parallel between human performance and non-primate performance. So the last thing I want to tell you about is sort of follows on this, that we've shown that the monkeys seem to be able to bring these memories to mind, so they're given more or less the equivalent of a blank piece of paper, and they can reproduce something they saw. But when humans are engaged in working memory tasks, what we see is that it's cognitively effortful, and those of you who still try to remember phone numbers once in a while, you know this fact that someone tells you a phone number. Well, what do you have to do? You have to rehearse it mentally. In fact, you use your phonological loop. You repeat the numbers in your head, and that performance is subject to distraction. So if someone starts talking to you when you're trying to rehearse the number, you're very likely to forget what's going on. So surprisingly, this is an issue. It's been addressed before in various animals, but it's very hard to get a clear answer on whether animals engage in some kind of active process or a more passive memory process. So we want to ask whether there's some evidence for active and cognitively taxing memory in monkeys. And we came to this design by a kind of a long route, so I'll just try to make it simple. But what we contrast here is in one set of conditions we're doing good. We present animals with a small set of stimuli, so it's just like the matched sample designs I showed you earlier. where on every trial there's one of these 4 images would appear as the sample, and at test they all appear, and you have to pick the one that you just saw. These are actually difficult in a certain way because of what's called proactive interference. You can get confused. Did I just see the duck on this trial, or did I see it on the previous trial, or the trial just before that? Because the trials are all compressed together, so your memory, they're all active in memory. So that's one feature of these small sets. But the other feature that we think is important about the small sets, and we got this from some other experiments that I can't tell you about involving list learning, is that we think that the small sets, because the images become very familiar, these images would generally be pretty meaningless to a monkey. They've never seen a fish before, or a duck, for instance. That would make them difficult to actively keep in mind because they don't mean anything to the monkey. But if we repeat them many times, they have these existing representations now of those items, and we think they might be subject to active maintenance because they're highly familiar. So we're going to contrast that with the exact same kind of stimuli, but that come from a large set of many, many thousands of these images that the animals don't see frequently at all. So they don't have this opportunity to develop a memory that would be subject to maintenance. So our argument goes, at least. You can see if you believe that from the data. So in one case, you think this is Abu, the monkey from Aladdin that Ben likes to use as his cartoon. When they're remembering these small set images, what we're proposing the monkey may do is actively keep that in mind. So he saw a fish, and he's keeping an image of the fish actively in mind, much the way we would keep a word in mind by repeating it in our head. In contrast, when they see these images from the very big set, they can't keep them in mind, and then they don't necessarily need to keep them in mind, so they just wait until they reappear at test. One of them will give a signal that that's a familiar stimulus. The other 3 will create a response indicating that they're novel, and the animal just can discriminate between which one's giving a familiarity signal and which ones aren't, and pick the one that gives the familiarity signal. One thing that we know about perirhinal cortex, both in monkeys and in humans, is that it responds to repeated images differently than novel images. You get a reduction in the response when you see an image the second time, kind of like habituation, and that's probably part of the mechanism that lets us recognize what we've seen before. So the idea is that if they keep these familiar images but not the unfamiliar images in working memory actively, then giving them some task during the memory interval that competes with doing that, like someone talking to you, would interfere with your memory for a phone number. This kind of competing task should decrease performance with the small set, but not with the large set stimuli, because the large set stimuli aren't being kept in mind anyway. Furthermore, this effect should depend on cognitive load. So how do we do this? It's a good question. How do we do that? See if I can get this to go. Okay, so again, you're getting familiar, if not bored, with the master sample design now. They see the fish at the beginning of the trial. A delay happens. Now, we have 2 different delays to try to equate the difficulty, because these infrequently presented items from the large set, they're easy to remember. So we test those at a 30-second delay. The frequently occurring images are hard to remember. We test those at a short delay. So then here you're seeing the test appear. Now you got to pick the fish that you saw before. Well, what do we do in the interval? We give them one of 3 different kinds of competing tasks. One is just a motor task, where a blue square appears in one of the 4 corners. The monkey just has to locate it and touch it. It should be low cognitive demand. A second type is passive perception. So again, an image appears in one of the 4 corners. It's just a random image, has nothing to do with the target or the test. They have to touch that. The third thing they have to do is they have to classify it, and so they report whether that is a bird, fish, flower, or person. And our monkeys are really extraordinarily good at this. They've been highly trained in doing that. Show you a short video of that happening. So these guys are very skilled in identifying. So you can see he does it quite quickly, whether it's a flower, fish, bird, or person. But this, we think, would be the most cognitive demanding kind of competing task. And so what we see is that, interestingly, that for the large set stimuli that are unfamiliar, performance is completely unaffected by these 3 different manipulations. This is when nothing happens during the interval. This is when they have to categorize. It just doesn't do anything at all to their memory. With these high-frequency images that we think they're keeping in mind, the more they have to think in order to do the interfering task, the more it interferes with their performance. So I think I should be summing up that I've hoped to show you that there are dissociations of memory systems for recognition and habit. That's what I showed you with that process dissociation procedure that Vicky does. I've shown you some tasks that use memory monitoring and suggest that those memories are accessible so the animal can tell whether or not it remembers. I show you that they can recall memories somewhat the way we do when we're given a test that just involves recall, where you're not asked to recognize items but to generate them. And then I hope I've shown you that interference effects indicate that in some cases, and not all cases, but in some cases, monkeys actively maintain an image in memory in anticipation of the test. So in summary, I think that many of the systems that we do have identified in humans through human cognitive neuroscience, that these are probably widespread adaptations that are shared by other primates. And the abilities to monitor and control memory may have been adapted for organisms many millions of years ago. That is, that they were present in the ancestors we share with rhesus macaques and other primates. So let me thank you for your attention.
I have a question regarding the small sets versus the large sets result. It seems to me there's some kind of confounding sense that the items in the small sets are presented a lot more times. So have you, for example, if you did an experiment where you have a large set of items, but some of them are presented more frequently, then you would be able to dissociate whether monkeys are getting selectively impaired in recalling those particular items.
Yeah, I think that's a direction that we're trying to move in, but it's actually, we're not sure how big of, how much they have to repeat. We actually do know that if we give them a new set of images and we just within 100 trials or so, they begin to show this interference effect. We know that we can get that, but we don't know how many of these they can actually have active at any one time. So if you think of it as a vocabulary, how many of these images can they keep as actively processable at one time? Yeah.
How large is your large set?
The large set is probably 3,000 images, and that works out that they do see them more than once in their lives, but not maybe twice in a month. Yeah.
I appreciate that you're doing artificial experiments on animals to specifically try and differentiate between kinds of memory. But the laboratory of life shows that animals have these unbelievable and incredible memories. India is famous for its stories of elephants with memories for individual people who've either saved them or hurt them. Elephantine memory is proverbial, right? Now you think of those mother penguins who migrate 50 miles, walk 50 miles across the ice to find their husband and egg after being 4 months at sea in the Arctic Ocean. They have to find that person. They can recognize individual emperor penguins in ways that we can't, right? Every animal memorizes the smell of its mother, okay? One of the fascinating things to me, and I think this is implicit in the kind of memory that we have as animals, not as humans, not as non-human animals, but just as animals, is that when we see something, we can rescale the memory of it according to its distance. It doesn't matter that the image we see is seen at this distance. We take it for granted that when the image comes towards us, we can see it's the same image. Because always we have to go away from and come back towards mother, father, family, the home, the cave, the lair, the den, as animals, okay? Another thing about memory, which is absolutely fantastic, is that animals can guide themselves around a huge district and they can remember where they've squirted their pieces of whatever it is fluid that they use. Have you in any way started to study these kinds of realistic memories, which aren't artificial memories, in the laboratory? Because they are incredible things that animals can do.
Yeah, so I agree that they're wonderful things that animals do. I think many of the things that you described, I don't consider them fantastic or unbelievable. I think they're believable and wonderful. And I hope I didn't give the impression that I meant to really give the impression that these systems that we're looking at, I think those came out of natural selection. That means that they served a purpose to those animals in their lives. But there's a real difficulty in studying learning and memory in the wild. It's because you don't have control over the experience that the animal has. That's why we do this in the laboratory, is because we can get control over the experience that the animal has. That's the only way you can really look at learning and memory in a scientific way. We can make observations, and there are many stories. But the last bit I'll say is, yes, we're very interested in looking at more naturalistic situations, and we are working on that a lot with particularly using video stimuli. And Kumadachi will be talking later on today. He'll show you, I think, some things along those lines that I think are really wonderful. So I think I agree with your comments.
Just a very quick question, back to the non-naturalistic but very informative types of experiments here. Have you looked at, or has anybody looked at, the capacity of working memory in monkeys? Because, of course, in humans we always have this magic number, whether it's 4 or 7, and so on. I seem to remember vaguely, and my memory's terrible. So I'm really interested in where monkeys outperform.
Yeah, all those kind of things, they're tricky to come up with any kind of absolute number because it's going to depend on the type of stimuli and the circumstance, what distractors are there, how motivated the animal is. But yes, certainly there are numbers of experiments. Jeff Katz has been doing some nice stuff in monkeys using a change detection procedure to look at memory capacity. Surprisingly, they find that the capacity is very small in that paradigm. Now, we've done other things that I alluded to, like list learning, where we present 5 items in a row, and you look at how well they remember them, and it doesn't give you a figure for the capacity, but it definitely shows you that it's limited. And one of the things that we show with those that's very similar to what you see in humans, although it scales differently, is that you get a primacy and recency effect. So the animals remember the first item best, and the last item best, and the intermediate items are poorly remembered. That's showing you a capacity limitation for sure. Yeah.
If there are no more questions, yeah, please be brief.
The extraordinary thing about recognizing things at different distances is that it means that the memory cannot be associated with the specific cells, because specific cells will only remember particular shapes of particular sizes. So in my opinion, and it may just be personal, the fact that you can recognize things as you bring the image towards you and away from you means that memory has to be stored in a scalable form. I don't know if this is in the literature, but it's my personal judgment. Now, this is true of every animal anywhere. This means, in my opinion, that all animal memory has to be stored in scalable form.
Well, there's certainly, I mean, that's the question of size constancy is one that's been looked at a great deal in psychophysics and in perception. It's not something I'm expert in, but there's a well-known set of information that helps you disambiguate the size of images, so you know it's not a small thing nearby. It's a large thing far away. I'm not sure I've thought carefully enough about how that interacts with memory, but certainly there are cells, that you can find in monkey temporal lobe that respond to the same image when it's presented at different sizes and in different locations. It has a receptive field the size of the entire visual field. Yeah.
One last question.
Many times human can believe or think in one particular way implicitly and behave explicitly in an entirely different way. In your experiments, have you found out any similar kind of things with the monkeys like this?
Well, we'd love to know more about that. I think we're at the stage right now where we're just happy if we can show that sometimes there's an explicit process and sometimes there's an implicit process, and then to look at these funny circumstances where they behave paradoxically. That's going to be trickier because sort of the way we go about demonstrating this now is by hypothesizing that they're going to behave sensibly rather than paradoxically. And if they were behaving paradoxically, we wouldn't be able to reach the conclusion that we are. So, but it's a great question. We'd like to know.
Yes, because I felt that this dissociation, if we are able to understand, then that will help us understand our human. We can understand how special we are, really, as a human being. So
that's a good point.
Thank you.
Just wanted to make two very brief comments. One, in line with what you were saying, there have been experiments, and I forget who had done them, who show that monkeys are able to also form associative memories. So they're able to recognize the tails and the faces of their familiar conspecifics and match them. So clearly, not only do they recognize images at distances, but they're able to also know that if I see your legs, that it belongs to that face for familiar individuals, which means that there are other high-level associations there.
Indeed.
The second point I wanted to make was there's a very fascinating study which was published about 5-6 years ago I think in the Proceedings of the Royal Society, which showed that wasps, social wasps, are able to recognize each other as individuals visually.
That's a fact. Yeah. So I mean, you can certainly. And I think that social wasps, that's a good example that you can look around and you see, well, there's animals that face the same problem. They're a very different animal, but they face the same problem. And in fact, they've evolved the same capacity. Whether it's precisely the same mechanism is probably not the case because the wasp nervous system and the primate nervous system are so different, but they have evolved the same solution that if they're going to live in a social group, they need to recognize individuals. Yeah. Thank you.